Well, it looks like I'm back now. So I'm starting a little bit later today. It's 8:30. My kind of pre-designed schedule was to start at 8. Unfortunately, today I had to do some work in the morning. I had a call from 7 a.m. and it went a little bit long till now. And I have a call right after this session is done. So this is going to be a bit of a shorter session than my normal 3-hour ones. And part of that reason I'm doing it this way is, I was doing it with more studying last week was just because sometimes stuff comes up and you can be super busy and you have to do that. So I wanted to take advantage of the time I had here. Hold on a sec. Let me just see. There's something wrong with the chat saying it's not connected. Let me just make sure that I am actually online right now. Yeah, it looks like I'm online. It looks like it's just, it's just the chat that's not working right now. So I can see the chat here now, but it's just not on this page. So it might be a little bit trickier for me to monitor it during this session. For some reason, my live streaming software was unable to connect to the chat. So I am back right now. What my initial intention to do today was for the rest of the week was to do problem sets in the morning and then do kind of more intuitive work or extra work to understand things later. Now, I do think that there's going to be some, there's going to be more work perhaps necessary on problem sets. So I think I might go into the afternoon as well today doing problem sets rather than just do the morning, especially because this session is going to be curtailed a little bit. But yeah, I think I'm good. So let me pop over here and look at what I have to do. My list here. So I've got this is notes from yesterday when I was working on the angular momentum. You know what? Actually, I might do the opposite. I might finish doing this stuff where I was doing and then do problem sets in the afternoon because that's going to be the longer session. And I do remember being in the middle of this last time. So let me just pop over and just see. Okay, good. We've got a few people watching right now. Christopher's asking, what are my thoughts on Anki? I love Anki. Anki is really good for learning memory-heavy classes. This is not one of them. I did make a few flashcards here, but I was thinking about it a little bit more, and as I went through it, there were less and less of these that seemed super relevant. So I don't even know whether I'm going to need those. That might have been a waste of time. I'm going to make more flashcards if I need them, but there isn't a ton of stuff to memorize because all the stuff that one would have to memorize pretty much is on this formula sheet, which would be through the exam. And realistically, like there is an important component to memory in math. Obviously, I have to remember how to do things, but that it's not the kind of flashcard memory, generally speaking, that a lot of the stuff you have to do is through practice. So the thing that I need to remember how to do is to do certain integrals or to remember certain tricks that I can do. But that is better practice through actually doing problems than through flashcards. So for math, I don't usually say that Anki is that useful, but it's really useful for languages, medicine, history, anything where you have to remember a lot of things, and that memory becomes the bottleneck for learning. So let me pop over. Jail saying is whether university education is necessary. Well, it depends on what you want to do, right? I think that a university education is certainly helpful for a lot of things. I have a university education. I went to University of Manitoba and studied a Bachelor of Commerce before I did my MIT challenge and stuff. So I definitely don't want to say that university education is worthless. And it's for a lot of professions, it's required. You want to be a lawyer, a doctor, an engineer, a scientist. It's almost impossible to do these jobs without having a college background. So that's just part of reality that you have to deal with that. Whether it's necessary, again, it depends on what you want to do. I do think that it is possible to become well educated without university, and it's possible to become really educated in subjects that you do not have a university background in. But that's somewhat of a separate question of whether it's necessary. So I think in this case, I'm confident that I can learn physics well without necessarily having a university background. It looks like there was a little bit of water spilled on my paper here. It's getting a little crinkled, but yeah, so I don't think it's always necessary, but I think that it can definitely help. And I definitely am grateful for the time I spent in university, even if I felt like it had flaws for sure. Krister's asking whether I find Anki counterproductive or detrimental to understanding. I don't think it's detrimental. Where I think it can be harmful is when you construe the task to do Anki instead of to do something else. So if you were to do like quantum physics and turn it all into flashcards and spend hours and hours and hours working on it, again, I don't think it would necessarily hurt your ability to do quantum mechanics. But if you're not doing what you really need to be doing, which is practicing math problems, then you may not be making as much progress as you think. So in that sense, it may be counterproductive, that it's not like an optimal way to learn things. But I don't think memorizing things is ever necessarily bad, but I do think it can sometimes create a false sense of security that you know something when really you only know it in a very narrow way. Again, memorizing, like if I memorize this formula sheet, I do think that it would probably aid me just because it would be at the tip of my fingers and I wouldn't have to go looking for it, right? But the reason I'm not memorizing is not because memorizing this would be bad, but because I'd rather spend my limited time practicing using it rather than memorizing it. So let me switch now. And I think, so I was working on this angular momentum, spherical harmonics stuff. And you know what? I was looking at this right here. This is, so sometimes what happens, you get some space from an idea and you recognize, oh, okay, I was doing this wrong. So I did this whole little Feynman technique on identical particles. And this is one of the benefits of having weekend and having time off, is that sometimes you get to incubate some ideas that, you weren't thinking about. And this identical particles idea, I'm just going to explain it out loud rather than do a normal Feynman technique. But essentially the identical particles idea is that it's just a brute fact of quantum mechanics that if a particle is truly identical, then we should expect its contribution. So let's just consider it this way. So we have a wave function that has two particles in it. And so normally the wave function would be a function of one variable x. We have x1 and x2. And this is, if we take the norm squared of this, this is equal to the probability of finding particle 1 at x1, or probability density of finding it at particle at x1, particle 1 at x1, and then this is particle 2 at x2. So that's what that means when you have these two values here. So the x1 and x2 are really independent axes for finding different particles. And the idea from this is that if we assume that, well, quantum mechanics would make so that identical particles are indistinguishable, then it should be the case that this, see if I can write things properly, that this should be this. That the probability of finding one at one position and the other position should be the same, because otherwise there would be some mechanism to distinguish them. And this really confused me when it was first brought up in the class, because it's a little bit like you're just sort of defining it by fiat, that it's like you're just sort of saying, okay, well, this is what identical particles are. Now let's try to derive some physics from it. And I think that confused me in the lecture, because really this is an empirical observation. It just happens to fit nicely with this idea that, well, if you imagine that they have this property, that they should be symmetric under swapping, that when you swap the particles, if they're identical, you shouldn't be able to detect anything about your physical system. So if they have this property, then this is good. And what I drew here, so I drew this thing here, and I was like, oh, well, these are the symmetric ones, these are antisymmetric ones, but this is not right. What I drew here is not right. Because, yeah, there is this kind of line axis, and then the symmetric ones are like, but this is not actually, because they're both everywhere, right? So, so what we're looking at here is that there's two ways this can be true. Because there's a square, when you square root things, you get plus or minus, right? So there's two ways that this can be the case, is that you can have a symmetric pair, and then that would be equal to some wave function of the first guy. So I'll just put x1, and then let's go chi x2. And then there's plus, and I'll just put plus or minus, so I don't have to write it all again, x2. And then we've got the 1 over root 2, just for normalization. So this idea here is that if we have a single pair of identical particles, then there's two ways that we can superimpose them so that they will maintain this idea that if you swap them, it shouldn't change anything about your system. So if we flip the particles, it shouldn't change anything. Because we only observe probabilities, which are up to a square, then this means that they should be, that they should be, that there's two ways that this could happen, because you get a plus or minus. It could be either they're half whatever square root times the x1, x2, and 1 over square root x2, x conditions. So this makes sense. And the thing was trying to get a visual intuition for this, because this actually embodies a lot of physics. Which one it is determines whether the matter is stuff that, like, my hands don't go through each other, or whether it's like light, which can actually benefit from being linked up together. And it was really confusing to me to figure out which one was which. So what I drew there is I drew this kind of thing, like this graph. And the idea here is that this is a graph, but it's not a two-dimensional graph in like two-dimensional space. Like, this isn't a tabletop. Rather, one of them is the position of one of the particles, and one of them is the position of the second particle. And the thing that I was drawing incorrectly is I was just assuming that I was just trying to draw like a height contour. So I was saying, like, these are our anti-symmetric particles and these are our symmetric particles. But this is not really that accurate, because, of course, the particles could be physically separate from each other or physically close, and that doesn't really, change anything here about them being symmetric or antisymmetric. The question is, what happens when you overlay these particles together like this? And what's happening is, if we consider a antisymmetric case, then I really should kind of consider this like a three-dimensional thing right here, because obviously we have some contribution. So one of them is going to be negative the other one. So we have, so it's very difficult to draw some of these things in quantum physics, unfortunately. But the idea that I was getting wrong here is that what is happening is that when you have the wave functions equal to the minus the other wave functions, that the antisymmetric case has to be 0 along this line, and then it's going to have some kind of contribution like this. So there's a kind of, it's not allowed here because it's one minus the other. One of them has to be flipped version of the other. Whereas in the symmetric case, this is actually twice the amplitude of this one here. So they have to be twice as much. I'm not able to draw this, unfortunately. I think that's one of my challenges with this, is getting the right visual intuition when you're dealing with like complex numbers in 3D space. So you have every single point has 2 dimensions on top of it. So it's like, how do you imagine these 5-dimensional things? Which is, I think, part of the challenge of trying to, draw stuff and think about things in this way, is that I've got 2 dimensions, but these are actually a 1-dimensional problem. It's not a 2-dimensional problem. So if we have, the symmetric case, let's say we have particle 1 was in the distinguishable case was here, and particle 2 was here, we have to kind of make it, so this would be the symmetrical case like this. And so we've got, this is the sort of symmetrical case we have here. Or we've got contributions from both sides here. And in these cases, because we're taking 2, this is going one of these and one of these. But these 2 here, because we're adding them together, they're constructively interfering. So these are twice as high as these ones are. Whereas in our antisymmetric case, well, what we're doing is we're having this. And this one would be here and here. So one of them's pointing up and one of them's pointing down. And because one of them is pointing up, one pointing down, there's nothing here, and there's nothing here. And here, this is where they are getting all of their contribution. And here, this is where they're getting twice the contribution here. So in terms of the normalization, the addition of these is only here and not here, even though, you know, separably, these are kind of, you know, the same essential particles, but one of them, they have to be minus each other in this two particle system. One of them, they are positive each other. So this is how we're getting the different system. This one here, there's twice as much. And this one here, there's, I think this is twice as well. Maybe it's more because of the normalization constant. I'm not sure. There's more, and then there's nothing there. So that's the idea I missed, is that I drew it like this, but this isn't actually the case that, well, it's here and here. They're actually overall 4 possibilities when we have these 4 separate. It's just that they're accumulated here a bit more. The antisymmetric are only here because they cancel out, and the key is to, you know, put them on opposite sides of this line here. So that was my visual kind of mistake with doing it last time. The other thing that I was struggling with a lot was this, which I thought would be easy, was this whole stupid thing about the why you can get real functions for this, why you can take the energy operator as real, whereas you can't for momentum. Because again, if you take this, you get the standing wave. And I was thinking about this a long time because I was trying to figure out what was it that I was getting wrong about doing this in this sort of calculation. And I think that the idea that needs to be kept here is that this energy, the value is equal to this, with the k coming in this e to the I, kx. Now this would be invariant under a plus or minus, whereas if we just had k kind of nakedly here, so e to the I h bar ddx, then we're not going to square whatever is here. And so it's not going to be the case here. Now, I couldn't figure out how to show it with the derivatives, and maybe that's just me making a silly mistake, because I tried to separate it all out, and I was getting minus terms that didn't match with positive terms here. So maybe there's some symmetry that I'm avoiding which causes these to cancel, and it's not obvious to me. But I think that this form of the energy being as represented as this k squared is the reason we can do this, because a negative number squared and the positive number squared. I do still think that that's related to this ddx, but I think it's only because of the form of e to the I something, right? Like, it's not just some of a general function that would necessarily be the case. So I still haven't like totally gotten comfortable with what's the precise mathematic proof of that, but I was feeling good about it. Now, I was working on this, understanding these angular momentum eigenstates, and I think, again, looking at the spherical harmonics was something that I didn't quite understand. And so what I want to do now is go through some of the lecture that deals with this particular concept of and so this was just sort of what I wrote down from memory. I like to do things from memory first, and then after do them from the lecture, just because I like to try to well, what do I feel like I know? And then where that helps you figure out where the gaps are of okay, well, what is it that I don't know? And so one of the things that I was struggling to understand is this three-dimensional picture of the spherical harmonics, which I think is valuable because this is, the shape of orbitals in hydrogen and things like that. I think also this sort of NLM dependence. I think I understand this here, this L and M and then the N, but it's a little bit fuzzy, and I don't feel like it's super comfortable. I'm super comfortable with it, and I think having a bit of a better visual intuition would be helpful, because whenever you're dealing with angular momentum and these 3D problems, it's important to like, okay, what am I trying to get? Because the math can be super complicated. You got 3 dimensions, you got a bunch of terms, you're doing spherical coordinates, you got sine thetas and r squareds and, you know, complicated triple integrals and stuff. And so it's better to have like, okay, base picture, what are we looking at, before you start trying to do crazy stuff with it. So that's what I'm going to do, is I'm going to focus on doing that lecture here. And I'm just going to, before I go, Jael says, alternating seems like a great way to learn. Are there any flaws compared to learning traditionally in school? Well, the ultra learning, I shouldn't say this, what I'm doing right now is, I wouldn't say that this is, well, all ultra learning looks like this. Ultra learning, in my definition, is intense self-directed learning. So self-directed means that the learner is the one driving for what you're doing. Now, it does not mean not learning in school. So very often when you are ultra learning, you may decide, I need a teacher, or I will learn best in this environment with feedback and with, you know, or I want to study under someone who really understands how to break down the subject. So given that kind of broad definition where it encompasses school, I don't think there's a real drawback to learning. Now, is there a drawback to learning this way rather than if I were an MIT student? Well, of course there are. There's already been situations where it would have been nice for me to ask a teacher or a peer, but I don't have access to them. There's already been situations where I don't have access to some of the resources that an MIT student would. So I definitely don't want to be implying by saying that, well, what I'm doing is a lot better than MIT students. MIT students have strictly more resources than I do. They have everything that I do, and more. So that's not the comparison I'm trying to make. The comparison I'm trying to make is that who of us can go to MIT? Who of us can get admission and go move to Boston and, you know, live in Massachusetts and study in this institution and, you know, pay all the tuition and get accepted? And very, very, very few of us can do this. So it's not really fair to like compare them like they're apples and oranges. For most people, it's this or something else. And I don't think that other thing is usually MIT. And so for me, I found that the MIT resources are so good that I found them better than some classes I did in my university. Not all, but some. And it may be better than other opportunities you have. So ultra learning is really about recognizing that there's a much greater scope of ways you can learn things and how you can learn with more limited resources and constraints than people recognize, and to take those projects yourself with your own initiative rather than, well, I can't attend MIT, so I guess I'm never going to learn it like that. And so that's really what I'm trying to do here, is showing one of those ways that those constraints can play out, not necessarily how all of them can play out. So I'm going to pop in this video. Now, I'm trying to remember which lecture this took place in. I think it was 16. Yeah, 16. So I think this is the whole lecture pretty much. Yeah, this is the whole lecture. So I think I'm going to go and just watch this one. I think I was watching it already. Let's see if I can pop on the video. Yeah, I was already watching this, and I think I was already taking some notes here. So let's go through and look at that here, and let me turn it on here. And I already have the lecture up. Watch this again. I'm going to just watch this through slowly. This morning I said I'm going to just finish doing these some of this conceptual work, and then the afternoon I think I'm going to do problem sets, because I'd rather have the longer session be devoted to problem sets. I've already done a lot of like this conceptual stuff.
H bar L plus. And for this term, L plus LZ YLM, LZ acting on YLM gives us H bar M plus H bar M L plus YLM equal to, pulling this out, this is H bar times M plus 1 times L plus. H bar M plus 1 L plus YLM. So L plus is raising the eigenvalue M by 1. This state, what we get by acting on YLM with the raising operator, is a thing with M greater by 1. And that came from the permutation relation. And if we had done the same thing with minus, if you go through the minus signs, it just gives us this. Okay. So, what does that tell us? What this tells us is we get a ladder of states. And let's look at what they look like. Each ladder, for a given value of L, if you raise with L plus and lower with L minus, you don't change L, but you do change M. So we get ladders that are labeled by L. So for example, if I have some value of L1, this is going to give me a value, this is going to give me some state. I can label by M. I can, well, let me put the M to the side. I can raise it to get M plus 1 by L plus, and I can lower it to get M minus 1 by L minus. Okay, so I get a tap. And if we have another value, a different value of L, I'll call it L2, we get another tower. You get M plus 1, M2 dot dot, minus 1 dot dot. So we have separated powers with different value of L squared. And within each tower, we can raise and lower by L plus, skipping by 1. Okay, questions? So that was basically the end of the last lecture. Said slightly differently. So now here's the question. So this was the question that the student asked right at the beginning. Is this tower infinite? Where does it end? No, I posed to you the question. Is the tower infinite or does it end? And why? Okay, so it's tempting to say it's infinite in one direction because... Okay, so it's because there are no bounds to the angular momentum one can have. That's tempting.
But at the same time, when you add the ratio operator on L, the eigenvalue elsewhere remains the same. So that you can't raise the z constant angular momentum above the actual.
Thank you, exactly. So here's the statement. Let me restate that. That's exactly right. So look, L squared is the eigenvalue of the total angular momentum. Roughly speaking, it's giving you precisely in the state while it tells you the expected value of the total angular momentum, L squared. That's a number, right? Now, if you add with a plus, you keep increasing the expected value of LZ. But if you keep increasing it, LZ will eventually get much larger than the square root of L squared. That probably isn't true, right? That sounds wrong. Right? That was the statement. Excellent. That's exactly right. So let's make that precise. So is the tower infinite? No, it's probably not for precisely that reason. So let's make that precise. So here's what we're going to do. This is a useful trick in general. This will outlive angular momentum and be a useful trick throughout quantum mechanics for you. I used it in a paper once. So here's the nice observation. Suppose it's true that the tower ends, just like for the raising and lowering operators for the harmonic oscillator in one dimension. That tells us that in order for the tower to end, the state must be 0 once we raise it. The last state. So y L, and I'll call this M plus, must be 0. There must be a max. Oh, sorry. Let me actually, before I walk through exactly the statement, so let me make first the no slightly more obvious and precise. So let's turn that argument into a precise statement. L squared is equal to, just from the definition, L squared plus Ly squared plus LZ squared. Now let's take the expectation value in the state while M of both sides of this equation. So on the left-hand side, we get a4 squared LL plus 1. And on the right-hand side, we get the expectation value of LX squared plus the expectation value of LY squared plus the expectation value of LZ squared. But we know the expectation value of LZ squared is a4 squared M squared. But the expectation value of LX squared and LY squared are strictly positive. Because this can be written as a sum over all possible eigenvalues of Lx squared, which is the square of the possible eigenvalues of Lx, times the probability distribution. That's a sum of positive strictly positive. These are positive guys. So LL plus 1 is equal to positive plus a4 squared M squared. And think of that tells you that it's greater than or equal to a4 squared M squared. Right? I mean, maybe these are 0. So the least it can be is, so that the most M squared can possibly be is the square root of L plus 1. Or most M. Okay, so M is bounded. There must be a maximum M, and there must be a minimum M, because this is squared. The sum doesn't matter. Recall that? Okay, so let's turn this into now a precise argument. What are the values of M plus and M minus? What is the top value of that of each tower? Probably it's going to depend on total L, right? So it's going to depend on each value. Let's check that. So here's the nice trick. Suppose we really do have a maximum M plus. That means that if I try to raise the state YL, I have state 0, which is not, and that ends the tower. So suppose this is true. In that case, in particular, here's the nice trick. L plus YLM, if we take its magnitude, if we take the magnitude of the state is 0. It's a 0 function. So what's the magnitude? 0. Okay, you might not think that's all that impressive an observation. Okay, but note what this is. We know how to work with this. In particular, this is equal to. I should have done this. It's equal to. I'm now going to use the Hermitian adjuvant and pull this over to the right-hand side. The adjuvant of L plus is L minus, so this gives us YLM. L minus, L plus, YLM. This also doesn't look like much of an improvement. Until you notice from the definition of L plus and L minus, but what's L minus L plus? Well, L minus L plus, we're going to get an Lx squared. So YLM. We get an Lx squared plus an Ly squared. I'm going to get my sign right, if I'm not careful. Plus. Well, let's just do it. Okay, so we have L minus L plus. So we're going to get a Lx ILy minus I Ly Lx. So plus I commutator of Lx with Ly. Okay? Good. So that's progress, YLM. But it's still not progress because the natural operators with which to act on the YLMs are L squared and LZ. So can we put this in the form of L squared and LZ? Sure. This is L squared minus LZ squared. YLM. L squared minus LZ squared. And this is, well, this is I H bar LZ times I is minus A bar LZ, so minus A bar LZ. YLM. And this must be equal to 0. But this is equal to, from L squared, we get H bar squared, LL plus 1. From the LZ squared, we get minus M squared, H bar squared. And from here, we get minus H bar M, so minus M H bar squared. Notice the name is worked out. And all of this was multiplying YL and YLM YLM, if it's a properly normalized eigenstate, which is what we were assuming at the beginning, is just 1. So we get this times 1 is 0. Aha! And notice that in all of this was n plus. We were working here with the assumption that L plus annihilated this top state. And so grouping this together, this says, therefore, h bar squared times pulling out a common h bar squared from all this times L plus 1 minus m plus 1 is equal to 0. And this tells us that m plus is equal to L. And if you want to be straight, put a plus on it. Ever recall that? There's a very useful trick. If you know something is 0 as a function, you know it's normally 0, and now you can use things like Hermitian adjoints. Very, very useful. Okay, questions about that? Yeah. Good. Okay, so where this came from was I was just literally taking L plus and L minus, taking the definitions, and plugging them in. So if I have L minus, L plus, L minus is just to write it out explicitly, L minus is equal to Lx because the n are observables in sort of Hermitians, which are self-renewing, minus I Ly. So L minus L plus gives me an Lx Lx, it gives me an Lx I Ly, it gives me a minus I Ly Lx, and it gives me a minus I, which is plus 1 Ly squared. Cool? Excellent. I'm just saving serious separation here. Good. Other questions? Yeah. This here. Okay, good. So here what I this I don't have here. So here what I said is, look, I've got this nice set of operators acting on YLM. I know how each of these operators acts on YLM. LZ gives me an A bar M. Minus 74 squared. LZ squared, L squared.
So this might be a good opportunity to make another little flashcard. Unfortunately, I had I have a couple blanks here. Unfortunately, I had a bunch of papers that I had cut for this, and then I had some water here and it spilled and wiped some of them out here. So I'm gonna do so L squared YLM is equal to, because I want to make sure I can remember these eigenvalues. So this is, and I think we have just discussed this, that L squared on YLM is L plus 1. So that's a good one to know. These over here on the answer side. And then we have the other one, which is LZ YLM equal to, just so I can remember the eigen states or the eigenvalues of these things, because that's going to be important. So it should be h bar m, right? Okay. Oh, h squared. Oops. H bar squared. H bar squared. Then this one is h bar m, I think.
Yeah, well, overall, that was just some number times YLM, which I can pull out here.
All right. So if I want to make more flashcards, I'm going to have to cut more paper.
Cool. Yeah. Good. The subscript plus meant that, look, there was a maximum value of m. So m squared had to be less than or equal to this. There's a maximum value than the minimum value.
I feel like I understood this fairly well. So I'm going to just skip ahead. Yeah, this is spin, and then I remember this stuff. I just want to see if I have.
That same state. So the uncertainty of Lx is guessed in M, where L is macroscopic. It's meant being momentum constant. It's just a choice of coordinates. There's nothing deep. It's just nothing shallow. It's just definitions. Tail, or deep at all, will be sensitive to the angular momentum of the constituents of the atom, and we'll see different spectra. So it's an observable property when you shine light on, gases. This is something you can really observe. So what this suggests is one of two things. Either these are just crazy. I want to know what these wave functions look like, not just the eigenvalues, but I want to know what is the wave function associated to eigenvalues little l and little m look like, y sub lm of the A listed and phi. What do these guys look like? So
Okay, here's where I wanted to go. Visualizing it.
So the first thing to notice is that we know that we know what the form of the eigenvalues and eigenfunctions are. If we act with LZ, we get a bar m back. If we act with L squared, we get a bar squared to L plus 1 back. But we also have other expressions for LZ and L squared. In particular, I wrote them down last time in spherical coordinates. So I'm going to work in spherical coordinates where the declination from the vertical is an angle theta, and the angle around the equator is an angle phi. Okay. And the angle 0 is going to be up in the z direction. It's just a choice of coordinates. There's nothing deep. It's just nothing shallow. It's just definitions. So when we're working in spherical coordinates, and in spherical coordinates, we observe that this angular momentum, just following the definition from R cross B, takes a particularly simple form. That's a typo. H bar upon I, d phi. Okay. And instead of writing, also writing L plus or minus because it's shorter, and also because it's going to turn out to be more useful. So this takes the form H bar e to the plus or minus I phi. D theta plus or minus cotangent theta d phi. Okay. So these are the expressions for L and L plus minus in spherical coordinates, in these spherical coordinates. So I want to know how YLM depends on theta and phi, and it's clearly going to be easier to ask about the LZ eigenequation. So let's look at that. LZ on YLM. Sorry. LZ on YLM gives me H. Oh, yeah. Oh, Jesus. When I write letters by hand, which, you know, it's basically when I write to my mom, all my H's are crossed. I can't help it. So this is like the inverse. It's been a long time since I made that mistake. You do the other. Okay, so LZ acting on YLM gives me H bar M acting on YLM. But that's what you want to act with LZ, so let's just write out the differential equation. So H bar M YLM, where M is an integer or a half integer, depending on whether L is an integer or a half integer. H bar M YLM is equal to H bar upon I d phi of YLM. Okay, using the opposite power of division and multiplication, I will divide both sides by H bar, and I'll multiply both sides by I. Okay, and we now have the equation for the eigenfunctions of LZ. Which we actually written last time. And we can solve this very simply. This says that, remember, YLM is a function of theta and phi. Here we're only looking at the phi dependent because that's all they show up in this equation. So this tells us that the eigenfunctions YLM are of the form of theta and phi.
Thanks, Rodrigo.
E to the IM phi times some remaining dependence on theta, which I'll write as P of theta. And that P could depend on L and M.
This one is theta, and this one is phi.
Cool? Now, already, before we even ask about the dependence on theta, the P dependence, we learned something pretty awesome. Look at this wave function. Okay? Whatever else we know, its dependence on phi is e to the IM phi. Now, remember what phi is. Phi is the angle around the equator. So it goes from 0 to 2 pi. And when it comes back to 2 pi, it's the same point. Phi equals 0 and phi equals pi are two names for the same point. Yes? But that should worry you. Because note that as a consequence of this, y lm of theta 0 is equal to, well, whatever it is. But, theta of 2 pi is equal to e to the I m 2 pi times p lm theta. But this is equal to, oh, now we're in trouble. If m is an integer, this is equal to e to the I integer 2 pi, 1. Yes, okay. You're supposed to share that point, it's like the closest identity in the world. So e to the I 2 pi, that's 1. So if m is an integer, then this is just p lm of theta, which is also what we get by putting in phi equals 0. So this is equal to y lm of theta comma 0. But if m is a half integer, then e to the I half integer times 2 pi is minus 1. And so that gives us minus y lm of theta and 0, if m is a half integer. Okay, so let me say that again in the same words actually, but let me just say it again with different emphasis. What this tells us is that y lm at 0.
I'm going to just look through because this is feeling pretty, I don't want to say obvious, but I don't really feel like I'm getting anything new that I wanted to get. So I'm going to look and see if there's anything in my textbook here because I might want to just get a different explanation. So let's go, let's see what they have here for spherical harmonics. Okay, it might be in chapter 10. chapter 10 here. What page is that? 425. So it might be here. See if they have spherical harmonics in the index. .484, 485. So let me see which chapter 484. Yeah, this looks like a different explanation, so I don't know whether it's going to cover the thing I want it to cover, but I am going to switch over away from that and back onto this, just because I think it will be perhaps more enlightening to look at it this way. I'm just gonna get something real quick. All right. So let's look here. So I'm going to just read this chapter right now on an angular momentum and see if this different explanation sticks a little bit more for some of the it doesn't look like there's a lot of visualization here, but at least for some of the kind of form of these spherical harmonics and what does it mean. So this right here is our Schrodinger equation. Well, this isn't our Schrodinger equation. This is our energy equation for classical particles here. Oh, I should move it over here. You know what? I gotta be more careful about making sure stuff appears on the screen. So this is our familiar momentum squared over 2m, and this is our angular momentum, where m also divided by this radius squared plus our potential. Trying to see if there's anything here that will give a so theta is the thing going around, right? Hold on a sec. And phi is the thing going around. Theta is the thing declining from the top. So let me see if I can try to draw these out. So that's what I wanted from the beginning. Let's switch this over here. So we've got a couple of these guys here, and they have a different sort of form. So y00 is just a sphere, constant So total angular momentum equals 1 in z direction equals 0. So we know there's 0 momentum in the z direction, but the total angular momentum is 1. And this is root 3 over 4 pi cosine of theta, which is the declination angle. So when pi is 0, so I'll just do a cross section here. So this is going to be our z-axis, and let's say this is our x-axis. This is going to be rotationally symmetric, and this is our theta. So theta is going this way. So cosine of theta is going to be, is it 1? Does it start at? Because this is saying is if it's cosine theta, then that's making something like this, right? It's going to rotate all around. And then these are going to be this 3 over 4 pi. No? This seems wrong. Is that the answer I had from this one here? Yeah, it is this. No. I had, yeah. No, I had this. What? That's a 0 angular momentum in the z direction. Oh, right, because if there's 0 angular momentum in the z direction, it means it's not spinning around here. So it's not spinning around this way. Because if it were spinning around this way, you would expect it to kind of flatten out. But it's not. It's like this. And there's no complex value here. So this is just the spherical harmonic doesn't have any time dependence. So it's just like a ball like this. I think it'd have to be moving, right? To have any sign of, it can't be just stationary. I guess this is rotating with a phase, but how is it rotating? It's not rotating around this way. I guess I'm just trying to wonder what this looks like. Yeah, what does this look like when it's moving? This is just saying that, like, for any value, we're going to get some point, and that point is going to rotate with So it's going to be YLM times e to the IE over h bar t, right? So this is defining the amplitude. And then it is rotating, but it's rotating with what? This phase, the energy. What does our what does this look like when it's rotating? So considering there's no R dependence for this spherical harmonic, we just have to consider some kind of direction that's getting pointed out from our sphere. So let's say this is our vector right now. What is happening to our vector when this is rotating? So it's going through a complex kind of, I need a better way of sort of visualizing the fact that these are complex numbers in 3D space, because they're not just rotating in some spatial dimension, they're rotating over the complex numbers. So if we take the real component of this, so if we just, I guess, just imagine the real component, then this is going to be cosine. So it's just going to be like it's shrinking and going this way and shrinking and going this way. So the real YLM times e to the I e over h bar t. This thing is doing what? Well, we have a bunch of directional points. So these guys that are pointing out in the xy plane aren't going to do anything. They're just staying fixed. This guy is going up and down. So it's going between here and here. And it would be nice if there was like a way of like some kind of output that could visualize this in 3 dimensions. Because all of these guys are just basically oscillating. Like it would be going like, right? That's what it's doing, sort of. Yeah, I don't know whether I'm going to be able to get a much better visual intuition without having some kind of computer program to draw it for me. And then let's look at one of these other guys. So this y of 1, 1 is going to be minus 3 over 8 pi sine theta e to the, this would be I phi. So in this one we have 1 total and 1 z. And what does this look like? Well, now we've got the opposite. So sine means we're going to be starting at 0 and then going up to a maximum and then going down again. So it's going to be 0 in this direction, and then increasing, and then decreasing again. And this is also modulated by this e to the I phi. So if we look at this top down, how does e to the I phi change? So each one of these vectors that's going out is changing. So let's do real. this right now. Its real value is going to be cosine. So like this. Oh. But it is complex valued. So I think what we have is sort of like a two-lobed thing, and it's spinning around like this. That's our, from the top. That's our one state. And then this state here is like this, but it's there. It's not actually spinning around this way. Each of these vectors is rotating. What does angular momentum mean when we have this complex value? It's, what is it? I h bar was d phi. I think this is something that I'd like to get a better visual intuition for, is how in 3 dimensions, because we know in 1 dimension, it's kind of like it's making a kind of a corkscrew like this. If we have just a simple kind of wave and a kind of corkscrewing, and this rotational thing is moving it forward at this thing. This is like that, except the vectors are not moving because the vectors are 3D vectors. They're like, I guess with this spherical harmonic, because we don't have any R dependence, you could consider like the rotation of the vector itself. So it would have like, but when it's negative, it's going to be over here. So I'm trying to think if that's maybe not the right way to think about it. Because when this goes to here, it's not going to pop out on that end. I don't know whether there's a good way to visualize this. But this guy, I think, is like, it's the 2 lobes, 2 balls spinning like this. This other one, it's not spinning this way. It's like each vector in space, it's like it's rotating. And this is hard to visualize. Yeah, I feel like for the 3D case, I kind of want to have almost a computer program to play with. I don't think there's any applets for this this thing, though. I think I remember checking yesterday. Well, I might just have to leave it like this right now. This would be a good project to do a little programming thing, but I think it's just going to be too much of a detour for me right now to really want to get into it. But I think definitely learning a little bit of like getting some Python graphing application would be nice for just like playing with some of these guys. Because they have an applet, but I think it was a MATLAB thing. And I'm just trying to think of what the right visualizing characteristic is, because when you have a vector pointed in space, as it is changing, as it is getting applied this complex number, what is happening to the vector? Because it's not rotating, in any 3 dimensions there. It's like each of the values is becoming complex. So when it is negative, it's going to flip to the other side. It's like it's going kind of inside out almost. Like this. Is that a good way of thinking about it? That like each of these vectors kind of pulling inside out. Like, is that how I want to think about, you know, as a, like they're kind of as they're rotating through the complex number, they're kind of like, and so this would be sort of like coming in and out like this. And this one here is kind of doing the same thing. But I think it's also, because it's got this EVI phi, because there's a complex component to it, I think it's rotating around like that. And then what is our 2 one here? Well, y 2, 0 is cosine squared phi minus 1. So when phi is equal to 0, this can be 1, 3 minus 1 is going to be 2. So let's just draw our thing again. And then cosine squared means that it's going to be 1 here. I think it's like this again. But minus 1 means that there's going to be some. It's not actually going to go here. It's going to go like this. Right? I think this is right. Something like this. Okay. And then the 2, 1 cosine phi sine. Now it has 4 zeros, right? Theta. So 0 here. And 0 here. And then e to the I phi. So this is spinning around like this, and this one here is, it's not spinning, but the vectors are kind of, Well, I don't know whether I'm going to be able to get a much better visual picture right now. Yeah, thanks for the time. Right now, just playing with the math right here. I think I'm probably going to leave it where it is for right now. This is something I'd like to return back to. I'd really like to work on some of the visual aspects of getting a better visual intuition of this, but I don't think I'm going to be doing it in the scope of this project. My goal was to try to get the mathematical structure down. I think that has to come first, and I'm going to work on that in this month period. And then after, I think I might play around with Python when I have a little bit more time to work on some of the visual intuition, especially if I had this idea of, after the project was done, of making a little like text or some kind of version where it would show some of the intuitions of these ideas without using the math. So I might play around with that a little bit after. But I think for right now, I'd rather focus on preparing for this exam and focusing on more on the mathematical end of things. Although this is interesting that you know, playing with this did help me a little bit in kind of what's going on here with this thing. Because when I saw this thing on the top first, at first I was thinking it's spinning like this, but it's obviously not spinning like that. That's where we know it's not spinning, because there's no Z rotation. So what were some of the other things I had on this list here? And maybe I can go through them quickly before I start going back to questions again. So I'm just gonna cross off this because I feel like I got that now. And identical particles, I'll cross that off too. So let's go through crystal momentum. I think that would be a good one to go through. And I am going to be ending this one a little bit earlier. Let's see if they have crystal momentum in this. Crystal momentum would be nice if I could have just a textbook summary. Let's see if they have crystal momentum in my corner. No. Let's see. Project in this book, and that's an example of like where me doing this final exam that has grades for could be tricky. Is just that you know, I'm studying crystal momentum right now. Maybe there's a different topic that, you know, they're studying helium atoms, or I don't know what it is. They're studying something else, which could make it hard for me to do this exam. So hopefully that's not going to be causing a problem. But I think we did those. Do I want to look at something else here? Could do crystal momentum. I think doing this R naught G naught thing would be better first because it's a bit smaller. So let me write it down first, and then I'll go back to the notes. My pencils are getting very dull. So let's see if I can remember what G naught is equal to. G naught is equal to, I believe it is V up here, L up here, here. I think this is what it looks like. See, I think I actually have that as one of my flashcards. Yeah, what is G naught? No, this is not right. To root of 2m v naught over h bar times L. Good example of why to do a little bit of memorization for things. So let's try to break this formula apart. So we know that G naught is proportional to L. I'll just consider the barrier case first. Increases. is proportional to the square root of V. So low barrier. High barrier. However, is okay. And then what else do we have? G naught is also proportional to root over the mass. So now this mass is related to this wavelength idea. So what was our original idea here was that our wavelength, is it K is equal to, there's a wave number. K is equal to H bar momentum is equal to H bar K, I think. Where's the other one? What was there? Momentum is equal to H bar K, I think. Yeah, an example of something that I should definitely memorize. All right. Right, H bar K is equal to momentum. So, which is equal to mass times velocity. So, more massive equals smaller oscillations. Is that what I want? It's 1 over. Yeah. Smaller oscillations. So if you have some particle and it's like this, then that is a more effective barrier than one that is like this. Right? I think that's right. So G naught is the strength of the barrier, And then, so G naught much less than 1, very small effective barrier, because thin, low, compared to mass. So this is like that, right? And then G naught is greater 1, very effective barrier, because should say thin. It should be. Oh yeah, this is thin. Yeah, because this is width. This is going to be wide, high, or compared to M. Okay. All right, that seems pretty easy now that I've gone through it, but I remember being kind of confused about that. So let's cross this guy out. I had some other guys here. Is de Broglie wavelength versus light? I think I understand that now. Crystal momentum. All right, discern. Do I want to do one of these things first here? Maybe reading delta functions. No, I think crystal momentum would be a good thing to go to. Matan is asking, what do I do with eigenvalues in linear algebra? So the eigenvalues, as I'm working with eigenvalues a lot, the eigenvalues are you can think of a linear algebra, you can think of matrices as being a transformation. Basically, they take a vector that's pointing in one direction and do something to vectors and point them in a different direction. So the eigenvectors of a particular matrix are the vectors that don't change the direction they're pointing when you transform them. So if you have the matrix that corresponds with rotating around a z-axis, it's only going to be the vectors that point straight up this way that don't change. And if you're thinking of two-dimensional systems, then if you're rotating, the vector is going to be some imaginary vector, because in a two-dimensional system, it's pointing straight up like this. Whereas in the eigenvalues are how much does it scale it. So a matrix that that let's say takes your vector and takes this, let's say takes this vector and rotates it like this and scales it like this. The question is, well, if it takes this vector and continues to keep it in this direction, how much does it scale it? So if the eigenvalue is 1, it means that it doesn't change the length of your vector. If it scales it, it's changing it. And if it has that can also have a complex component as well to it. So when I'm dealing with these things, I'm not dealing with matrices and those kinds of linear algebra transformations. I'm dealing with eigenfunctions. So instead of just being a vector, which is 2 values, it is something that has a value for every single number. And so our eigenfunctions mean that when you apply some operator, which takes one whole function and turns it into another whole function, which thing spits out the same function with some scaling factor, and then the eigenvalue is the scaling factor. And that's important in quantum mechanics because the scaling factor is often the thing that you're measuring. So these transformations correspond to measuring the system, and the eigenfunctions are the kind of state that corresponds to a definite value of that thing. So a definite value, position, momentum, energy, angular momentum. And the eigenvalue that you measure is the observable. It's the amount of energy it has. It is the position of the particle. It is the momentum. So eigenvalues and eigenvectors are very interesting things. They were very confusing when I first learned them. So if you're struggling with them, don't worry. But the right way to think about it in terms of matrices or in terms of linear algebra is that a matrix corresponds to changing something. It's like you put it in one way and it comes out another way. And the eigenvalues are the things that don't change other than by a factor of scale when you put them through the transformation. The eigenvalue is how much they scale. All right, let me, I want to write crystal momentum. So let's see if I can just try to write down everything I know about crystal momentum right now. I may not finish it. I do have to take a break earlier today because I have some work calls coming. Momentum. I don't know why I can never spell momentum. I always want to write a momentum. I don't know why I can never spell momentum properly. But yes, I do have a call that's going to be coming up, so I'm going to have to end the morning session a little bit earlier. But let's try to get through as much as I can on this. And then once the once I get back this afternoon, I think I will probably resume directly with problem sets. And so I might not get through all of crystal momentum right now, but I'm going to be working on earlier problem sets, so I'll tackle it tomorrow if I don't have time. So let's see how much I can remember for crystal momentum. So we have h bar q is our crystal momentum. Momentum. Oh man. In the way that h bar k was key for our free particle. Note, this is not a true momentum for our particle because is not in a momentum eigenstates. Not in a momentum eigenstate. So what else do I know? Well, we have a periodic lattice. Periodic lattice. We can construct energy eigenstates are also periodic. What else do I know about the crystal momentum? So EQ is energy dependence on Q on the same way that EK is equal to h bar squared k squared over 2m. But this is not going to be, in general, such a simple function. What else do I know about the crystal momentum? Less than I realize. What else can I say about it? Well, I can say at the top of the band will approximate free particle it will be different. That's right. Like we have so I think we have kind of like that, right? What else do I know? All right, let's look at the notes and see what I can recall from looking at the notes now. Here at the end. All right. This is lecture 22. P covers the x dependence of the phase in psi. Q governs the phase x. So that's all right. Phase dependence. Okay. Yeah, that makes sense because you have e to the ikx. So this is our, phi x is equal to kx. Okay. Q phase in x for our periodic lattice. So ddt h bar q. So we'll just consider a wave packet. At q naught equals the expectation of the force. So we have psi q equal to e to the I qx times u of x. And this is going to be a periodic function. Some periodic function, some spatial phase dependency right. All right, this is small gaps, this kind of thing. Is that it? Is that it for crystal momentum? Oh, we had Q from here as well. So lecture 21, I think I want to look at. So I think this has to do also with our standing wave group velocity stuff. So this might be useful to rewatch. Oh, sorry. Someone's asking me, where can I get my notes? Well, I'm going to try after this project's done to scan these notes and put them as PDFs. I don't know how useful they're going to be. I mean, these are just my notes. Like, they make sense to me. They're for my purpose. I'm not really making teaching guides here. If you want to use these resources, a textbook or the materials for the class are going to be a lot more useful. But if you're just sort of interested in how I'm taking notes, then that's fine for sure. So I think what I'm going to do is jump over to lecture 21, go through it a little bit more slowly and see if this sinks in a little bit better. Because I think some of it was that I was missing a little bit this group weight phase stuff from 803 that I've now covered. So it might be a little easier now. So I'm going to just do 21 and maybe 22, kind of a second pass. And then we'll just sort of see how it goes. So I'll pop over here and let's go 21, 22.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu. Okay, so we're going to pick up on our study of periodic potentials and our search for the explanation of the physics of solids. And I want to quickly remind you of the logic of we went through last time. This is one of the more subtle bits of logic in the semester, so I'm going to do it again. A little faster. I'm also going to do study for form. I want to think for a moment about just a free particle, but I want to use all the language and formalism we used for the periodic potential last time, translation operators, block wave functions. I want to use all of that for just a free particle. So first, let's just remind ourselves how the free particle story goes. So for a free particle, by which I mean the energy operator is p squared 1 2m, and no potential plus 0. We have a very important consequence of being free, that the energy can be written as just p squared, which is that the energy can use with the momentum operator. And what this tells us is that we can find a basis of eigenfunctions, which are common eigenfunctions of E and P. Right? We can extend every wave function, any arbitrary. Fantastic, thank you, sir. We can so as not to. Oh, brilliant. Thank you, sir. I don't know. That's an awful huge straw. Pay no attention to the device beneath the table. So, because quantum mechanics, right? Bowl of water. So the energy and momentum commute, and as a consequence, we can find a basis of eigenfunctions exists. A basis of eigenfunctions, which are common eigenfunctions of E on phi E, L label K by the eigenvalue of K is equal to E phi EK, and P on phi EK is equal to 8 bar K phi EK. You'll notice, of course, they don't label by the eigenvalue, but they label it by something that's determined by the label. The eigenvalue is determined by the label 6 bar K. Now, here's the thing: can we allow E and K to be any values we want independently? Can I make E3 and K 47? No, I need to make, there's a consistency relation which involves satisfying the energy eigenvalue equation. We actually have to find solutions of these equations. And once we find the solutions of those equations, we'll find relations between K and E. And in particular for free particle, we find that the relation that we need is E is equal to n over E sub K is equal to h bar squared K squared upon 2m. This is also known as omega is equal to h bar K squared upon 2m. Just to remind you, to the right, E is h bar omega, E sub K. That's not the thing I wanted to look at. This is. And if when we work this way, we find that the energy eigenvalues, E, as a function of K, take a determinate form, and that determinate form is quite simple. It's a parabola. Ever go with that? So if you know K, you know E. But if you know E, it turns out it's doubly degenerate. So if you know E, you're one of two Ks. You could be either E IKX. And I needed to say that the function, so from the solving the equation, gave us that the energy eigenfunctions phi EK are equal to some normalization over 2 pi. It's conventional E to the IKX. Okay. So if I tell you the energy, you don't know which momentum state I'm talking about. But if I tell you the momentum, you know the energy. So there's a little degeneracy. That degeneracy is coming from parity symmetry of the system. And note that what we've done here, that we have to write the wave functions in terms of the IKXs. Is there another basis we could use for the energy eigenstates? Yeah, because these are degenerate, we could have taken any linear combinations of e to the IKX and e to the minus IKX. We could have got, for example, sine and cosine. That would have had the advantage that the energy eigenfunctions would have been pure real, which is when we proved was possible. You can always choose pure real energy eigenfunctions. However, it would have had the disadvantage that these states would not, sine and cosine are not eigenstates momentum. Right? It's convenient to work with common eigenstates momentum and energy, so we give up on having a real wave function, and that's the cost of finding shared eigenfunctions of energy momentum. Ever go? Any questions? Okay, so this is the usual story for the free particle, but we learned a couple of things about it immediately just by looking at by eyeballing the wave function. We see that, so some things to note. Note, all states, all eigenfunctions, E, which are on the form e to the I kx, I'm going to add the time dependence in now, minus omega to kt, are extended. Right? They have equal probability density everywhere, and the probability distribution does not fall off to zero as we go far away. And so what this tells us we have to do is we have to build, if we want to study real localized states that are localizable, that are normalizable, we have to build wave packets. Okay. Of the form psi is equal to integral dk, the sum over all momentum modes, f of k, e to the I kx minus kt, k, where this f will generally take, well, we don't have to take the real function, but is peaked at some k mod. This is what we get when we study the evolution of a wave packet of this form. But in particular, such wave packets have a couple of nice properties. The first property we studied, and if you're not totally comfortable with the idea of group velocity, you really need to go over it again. It'd be an excellent thing to show in recitation, for example, stationary phase. So the group velocity of such a wave packet, as long as it's of this form and peaked around a single momentum value, k naught, the group velocity is d omega dk evaluated at k naught, at the peak value of the distribution. And note, I want to just quickly note that this is equal for the free particle to, well, omega is h bar k squared upon 2m, taking with respect to k, the 2 cancels via h bar k upon m, h bar k upon m, which notably is equal to the expectation value of momentum over the mass. Ever recall that? So this gives us a nice way to, by the way, if you didn't know the mass, but you could measure the system. For example, if you compute on average momentum, you can compute the group velocity if you're watching wave packets move. This is a nifty way to compute the mass. The mass can be given by, well, put the mass up here and divide by the group velocity, measure the momentum, and divide by the group velocity. Okay, so I can take this and notice that this just exactly used to be the mass. Okay? So this is a way to given a system with momentum and a group velocity, I can compute an effective mass, which for the free particle is just the mass. Cool, just a side observation. But this is all a consequence of the fact that we have wave packets of this form. Their plane waves are at least things that have a phase times what could be a real, an overall phase of the whole thing, a real function which is peaked at a particular value of k naught. The usual wave packet story. Any questions? So this should all be pretty familiar. Now here's the thing. When we talk about a periodic potential, what I want to do next is I want to talk about a periodic potential. So now we have a system that has maybe steps and it's periodic with period L, okay, and then ditto. It's going to be periodic. And I want to run through the same analysis. I want to find the energy eigenfunctions. I'm going to organize them in a nice way. And in particular, I want to know the following. If this is equal to v of x, and v of x, and I call the energy operator, E sub g, is equal to p squared upon 2m, plus a coefficient g times, what we call g sub naught, which is unambiguous, times v of x. Notice that when g naught is 0, this is just the free particle. And I added a periodic potential times 0. That is stupid, but doable. But as I slowly turn on g naught, what's going to happen? The energy eigenfunctions are going to slowly change, and the energy eigenvalues are going to slowly change. And the actual system we care about has an actual value, like 7 or 3 or whatever. But this is a way to connect the free particle to the particle in periodic potential. You know, if you just count a little weak potential, you don't expect the system to radically change. So one way to organize the question of periodic potentials is what happens if you slowly turn on this periodic potential. Okay. But here's the first thing I want to notice. The first thing I want to notice is that it's no longer true that the energy commutes with momentum. So it would be silly to try to organize our wave functions in terms of energy eigenfunctions, which are also momentum eigenfunctions, because that will only be a sensible thing to do when this interaction term, when this potential is 0, right? So instead, I want to organize them in terms of energy eigenvalues and any other operator that commutes with the energy eigenfunction. In particular, this is not invariant under arbitrary translations, which it would have to be invariant under integral method. But it is invariant under translations by L. And as a consequence, we have that the energy operator commutes with translations by L, where translations by L takes a function and shifts it over by L. And so, because translations by L, as we showed in our problem long ago, commutes with p squared, because this is just an exponential of LP with coefficients, with 9 and h form. And because the potential is invariant under shifting by L, and so it commutes with TL, this is 0. So what this tells us is we can find common eigenfunctions. In fact, a common eigenbasis of E and TL. And here's the thing that's nice about this. I could have made this argument whether the potential was 0 or not. For the free particle, it's also true that the system commutes with translations by L. It's free. There is no potential. It's sort of silly because I could have just used the momentum. But let's see what happens if we use the translate by L. Ever recall that? Okay, so we want to find common eigenfunctions. So as you guys showed on a problem set, the eigenfunctions of TL. So in order to do this, what are the eigenfunctions of TL? You showed that the eigenfunctions of TL must take the form. Phi sub q of x is equal to e to the I q x to q of x for some q, where q is where u is a real periodic. I don't really need real, but it's going to simplify my life, so I'll take it to be real periodic function. Well, let's drop real because we do that. Where u is a periodic function, and phi of q is this phase. It times the periodic function. So in particular, phi is not periodic. As a consequence, TL on phi q is equal to e to the I ql phi q. Because this guy shifts and this is invariant. It's periodic. Okay. So this is the general form of the eigenfunction to translate by L.
Yeah, this is 1.5 times, I think.
Okay. Periodic means u divided by cell. Okay. So what this tells us is that the energy eigenfunctions.
I have watched this before, so that's part of the reason I'm watching it a little bit faster. I don't think I watched it at 1.5 the time before. I'm just trying to watch for things that, well, I'm not sure exactly what I'm watching for right now because this is just sort of an overall section, but I've learned some things since, so I'm paying attention a little bit more now.
Can be organized as phi sub e q. So it's an e active q is equal to e.
Let's see if I got this right. So we've got our Q. This is this X dependence. So we have, excuse me, some periodic function. You know, hypothetically, something like this. This is our U. Let's say, then e to the I q x u of x. Need this, but there's going to be some complex phase associated with this. So when does this rotate? This rotates on Q. It's equal to 2 pi. So we have here, let's say this is our L, and then Q over 2 pi. 2 pi, which is, I'll just call this like lambda wavelength Q. So let's say this is this. Let's say this is. So that gives us something, I don't know, there's going to be some kind of complex pattern that's going to emerge because of that. And So it should be periodic in Q times L, possibly less. But there's some common factor. Okay.
Just like this one, phi sub EQ, and TL phi EQ is equal to ECIQL phi EQ. It's just saying that we have common eigenfunctions, with energy E and TL eigenvalue Q. No, because under translation by L, this x goes to x plus L. Oh, I slightly changed notation from earlier in the course. You're right, I slightly switched. So, good. So, yes, so, thank you. So let's fix notation. TL takes f of x. So, f of x minus L is what we used previously. Right, but I'm going to just switch notation and call this f plus L. So for all the notes in here, this is f plus L. It doesn't really make a difference. You just have to be consistent. And you're right, I switched between lecture, 8 and this one. So that. Good catch. Thanks for pointing it out. Okay. So in which case, this is just by x to f plus L and give you the IQL. Good catch. Good. So again, we have this property that we can find common eigenfunctions. However, can E and Q be specified independently? We know on general grounds that it's possible to find eigenfunctions which are common eigenfunctions because these guys commute. E and TL commute, so we can find common eigenfunctions because there are. And meanwhile, we know that the form of these eigenfunctions is of this form because any eigenfunction of TLs of this form of phase times periodic function. Does that by itself tell us the relationship between the eigenvalues E and Q? No. Right? Just like E and K were independent until we solve the actual eigenvalue equations. Right? And it required things like regularity and no singularities. So what we have to do at this point is solve the differential equations for continuity, periodicity, and solving the energy eigenfunction, energy eigenvalue equations. And when we solve the equations, we'll get a relationship between E and Q. Okay. And in particular, if we do that here, here for, so do you want to do it this way? Yes. So in particular for write this in the following way, for g equals 0, g not equals 0, which is a free particle, we find E is equal to h bar squared q squared, E sub q is equal to h bar squared q squared upon 2m. And and the wave functions are the form phi sub q, E are equal to the normalization over 2 pi times E ci q x. And the coefficient function u is just constant, which is nice. So it's nice constant. And so this is reassuring because it's exactly the same form of the wave functions with exactly the same form of the energy. But we're here, the value q is representing the possible value of this concluding eigenvalue TL. So there's a question.
Yes. So for the translation operator, that the IQX convection will work for any complex Q and any Q with grayed out, or any periodic Q with grayed out.
Yeah, although if Q is complex, then this is badly non-normalizable because if Q has an imaginary part, then that function is going to diverge in one direction or the other. So Q better be real. So that's correct. This expression, a function of this form, a periodic function, periodic with period L times an E to the IQX, for any real value Q and any periodic Q will be a function that will be an eigenfunction of TL. Translation. No, it's not just non-Riche. It's in fact unitary. I mean, what is that your question? Sorry, this is
so then just the translation operator has a really large number of eigenfunctions.
Indeed it does. And that number is the same as the number of momentum eigenfunctions. Because they can be both used as a basis. They're both operators whose eigenfunctions form a basis. That's exactly right. So I think the difficult thing is to think that we tend to think that there aren't very many momentum eigenfunctions, for example. But there's enough momentum eigenfunctions to be a complete basis. So if this seems like a vastly larger set, then indeed. Okay. So when we do our analysis for the free particle, this form we get the same story. And I want to point out a couple of consequences for this. Working with this TL operation, working with TL eigenfunction, we have exactly the same properties. Our eigenfunctions are again extended. We have to use wave packets, and those wave packets move with the group velocity, which is given by d omega dk. On the other hand, here, when we write superpositions, our general wave function, our general wave packet, I'm going to write here, psi is going to be of the form integral dq of e to the I qx u of x times some f of x, or sorry, f of q. Use of q. Okay. So as long as this is a periodic function, then and I should say minus omega sub q t to get the time dependence in there. As long as this is a nice periodic function, especially for this case when it's real, and this is a sharply peaked function, which is sharply peaked around some q naught, then we will find that the group velocity is again d omega now dq evaluated at the peak value q naught. And that's just a general consequence of this form of our wave packet. As I encourage the recitation searchers to review of my stationary phase in the.
Hold on a sec. So let's just remind ourselves here. The G is again the omega dq q naught stationary phase, and so we still have the same group velocity of how our, so Q still, linear planning, linear programming. I did do a little bit of the very high level, the algorithm for, I think it was for solving linear planning systems or linear programming systems in one of the MIT algorithms classes. I could not tell you very much beyond that at this point right now. I think it depends on what you want to do it for. I think most of the practical applications is just there is an algorithm for solving it, but it's complicated. So you just plug your things into some system and it'll just solve for the min max you want to do. So if you're doing like management science or something, if you're going to doing it from a programming standpoint, I believe there were 2 algorithms classes I took in MIT, and it was in the second one, I think, that they covered it. But if you get a book on algorithms, they should explain how to do it. I seem to remember the algorithm not being, I think I want to say it's NP complete in the extreme, but that the average case, I think you can have a polynomial time algorithm. Wow, this is really coming back though. So I don't trust me on that.
And secondly, again, we can find this nice notion of mass, which is the expectation of momentum divided by the group velocity. And again, this for our simple free particle, this is just a nice way of measuring mass if you happen to want to do so for your free particle. No one told you the mass. Remember that? Okay. Questions? Yeah.
So when we have G naught not equal to 0.
Excellent question. So now let's study the case with G naught not equal to 0. Okay. So far we looked at for G naught not equal to 0. That was just this line. So everything else was for general case of studying common eigenfunctions of E and TL. So now let's study the case for an actual periodic potential. So in particular, repeat for G naught not equal to 0. And this is the analysis we did last time. We did exactly this analysis, and we looked for the common eigenfunctions of E and translate by L. Right? And we found that the common eigenfunctions took the form EQ is equal to e to the I q of x times some u of x. And now we need to find what's the relationship between E and Q. Are any E and any Q allowed? And do those give you eigenfunctions for the free particle? We expect that's certainly not the case. On the other hand, we have a guess as to what it should look like. The energy eigenfunction for, let me actually write this here. Oh, whoops. The energy eigenfunctions and energy eigenvalues, more importantly, of the free particle organized in terms of Q. We just immediately see the energy is just a per squared q squared upon 2m. So the potential, or sorry, the energy as a function of Q is again a parabola. Okay, so here's Q, and here's the energy. This is for free particle. Right? Free particle, E equals h bar squared, q squared upon 2. Now I'm going to ask what happens as we slowly turn on the potential. So we think G naught equals 0. So we did this last time. We turned on the potential. We turned on a potential which is in fact delta functions. So now in order to solve the differential equation, we have to actually know what the potential is. So no getting around it. And so we took a bunch of delta functions with dimensionless strength G naught and space by L. And what we found was an equation relating E and L, which took the following form. For simplicity, I'm going to write E is equal to, this is purely definite, this has nothing to do with momentum, although it looks like momentum. I'm just going to write E formally as h r squared script k squared upon 2m. So k here should just be understood as root 2m over h bar squared, which I hate writing out over and over again. So let me actually write that the other way around. Script k is equal to the square root of 2m e upon h bar squared. So when you see k, think e. When you see lions, think lions. Okay, so So we found that the condition, in order that we solve the differential equation, the condition in order that E and Q label energy eigenstates, which actually are energy eigenfunctions, common energy eigenfunctions of the energy and the translation by operator, we found that there was a relation which was cosine of QL is equal to, let's do cosine of KL plus G naught upon 2 KL sine KL. Right? So first of all, let's make sure that this agrees with what we found when G naught was equal to 0. When G naught was equal to 0, we found that E was equal to a per squared Q squared for any Q. And well, when G naught is equal to 0, this term goes away, we get cosine of QL is equal to cosine of KL. And an example of a solution for that is QL is equal to KL, or Q is equal to K, in which case E is equal to a per squared K squared upon 2m by plugging in that expression. Cool? So this reproduces the free particle result when we need it to. But in general, it's not the same. So what does it look like? So let's take a look at that. So here, first off, what I'm plotting here is the plot that we drew on the board last time. Only here I'm plotting horizontally is the energy, okay, E, and vertically is cosine of QL. Now for Q, a real number, cosine of QL goes between 1 and negative 1. And so there's any value in here corresponds to a valid value of cosine, or of Q, sorry. So any value, any point between 1 and minus 1 is an allowable value of Q. So for example, this point right here corresponds to this value of Q, okay, just horizontally.
I'm going to skip ahead a little bit. I feel like this part I get.
And watch what happens to these curves. Totally fine. Right. Look at that mistake. Ever see that? Press it. String. The fact that those scatterings of one down and one much deeper down, if those interfere, I can mention one direction or the other. Okay. So we see that the eigenfunctions are all extended, and so as a consequence, we have to build wave packets. So therefore, we must build wave packets. And again, the form of the wave packets, psi is equal to the integral dq f of q, sorry, I'll say f q naught, sharply peaked around the point q naught of q, and then the wave function is e to the I qx minus mu t times ru of x. So q. Okay. So we have to build wave packets. So 3, this tells us that those wave packets move with group velocity by the same logic as for the free particle, and the group is equal to d omega dk, or dq, evaluated at q naught. Where q naught is where our wave packet is sharply peaked. So that's already telling us something really cool. Look at this lowest band. Okay. Let's make this a little more reasonable. So let's look at this lowest band. Let me just make this big. Okay. Let's focus in on the lowest energy band here. So there's the lowest energy band. It goes from the top of the band to the bottom of the band. It's just a little bit away from the free particle because we're looking at a relatively weakly perturbed system. It shows a small value of Q naught. Actually, let's make it a little more exaggerated. Okay. So there's the free particle curve, the red one, and the blue one is our actual band. So that's the energy as a function of Q. Now let's make it even bigger. This one goes for low. Let's see. Okay, and so what you can see is the following. It looks sort of like parabola at the bottom, and at the top, it curves over and actually goes to zero derivative. And it has to because it's got to be periodic. Because Q is periodic with period 2 pi over L. Okay. So what does that tell you about the velocity? Well, let's look at the velocity, the group velocity, a wave packet with, let's say here's 0, as a function of Q, okay, between minus 2 pi over L and 2 pi over L. What is the group velocity? Here's what I mean. What I mean is, let's build a wave packet which has a reasonably well localized momentum, say at this value of Q. So I build a little wave packet that has its peak here, and what does that wave function do? It has a group velocity, and the group velocity is given by d omega dq. And now we can't solve that equation analytically because it's transcendental, but we can see just by eyeball what this does. When Q is equal to 0, what's the group velocity? Yeah, it's the slope, right? D omega dq. So what's d omega dq at the origin? 0, right? Because it's just horizontal. So it's 0. Good. What about what about a little bit to the right? What if I give a small positive Q? Wave packet localized with a small positive Q. It's got a little bit of a slope now, right? A little bit of a positive slope. So it increases, but then it reaches a maximum slope halfway through the domain. So here it hits a maximum value, and then the slope comes back down. And if we went the other way, if we make Q a little bit negative, the slope becomes negative, and that's the velocity. So that's a slightly strange thing. As we increase Q, it increases the velocity. Increasing Q increases the velocity for a while. That's just like K and momentum. Momentum is h bar K. So that would be increasing the group velocity for a free particle. But now as we increase the Q a reasonably large value to pi upon L, oh sorry, this is pi upon L and pi upon L. So if we do this to pi upon 2L, or roughly, in the middle we get to a maximum value. And if we increase Q further, what happens? The velocity goes down. Or if we increase Q further, the velocity goes. It's a string. For free particle, if you have momentum h bar K and you increase K, what happens to the expectation? What happens to the group velocity? If you increase the momentum, what happens to the group velocity for a free particle? It's going to increase, right? But not for our particles, not for particles in the periodic potential. The wave packet, as you increase the crystal momentum Q past this maximum, as you increase the crystal momentum, you actually increase the velocity. And in fact, if you keep increasing Q, eventually the velocity goes to 0. And you increase Q a little more, and it actually goes negative. So this is a funny thing. It's not behaving like normally you think of as momentum. And indeed, is there momentum conservation in this system? No, we have a periodic potential. There are forces at work. Is momentum conserved? No, it's not a system that conserves momentum. Momentum can be exchanged between the particle and the potential. Q is a good quantity. It's the eigenfunction of TL, and that does commute the energy operator, so it's a perfectly reasonable quantity. But the momentum itself, P, is not conserved. So this crystal momentum Q is not the momentum for all these reasons. But it plays a lot of the same role, especially near the bottom of the band. Near the top of the band, it's a little bit funnier, because if you increase Q, you get a negative velocity. If you decrease Q, you get a positive velocity. It's exactly the opposite of what you normally expect. But let's hold on to that thought for a second. Okay. So there's another sense in which the crystal momentum is like a momentum, and you're going to show this on your problem set. But it's very important in giving you some understanding, some intuition about what the crystal momentum is. On your problem set, you'll show the following. Suppose I use a constant force. For example, imagine this particle in my periodic potential had a charge, and it's generally a constant uniform electric field. Then that particle experiences a constant uniform driving force, which I can write as a linearly increasing potential. Right? So what you show in the problem set is that the force, the expectation value of the force, is equal to, for a wave packet sharply localized around some value Q naught, the force, it gives the time rate of change, ddt, of the expectation value of Q. So if you turn on the force, what happens is Q increases linearly. Thank you. It's so hard. It's just so obviously one. So the force increases. So the force is constant, and h bar Q increases constantly. So Q just increases linearly in time. Yeah. But that's funny. Well, we'll come back to just how funny that is. It just is. Yeah. No. Well, let's think about how funny that is. Let's tackle this right now. So imagine we start with a wave packet which is well localized around 0 crystal momentum, around Q equals 0. Then what is that wave function doing in time? How does that wave packet move? What's its curve velocity? 0. So it's just sitting there. It's just a little wave packet slowly dispersing. Yeah. But if we don't make it too tightly constrained and too tightly constrained, the dispersion can be made quite slow. So it's just a little wave packet localized around particular position and localized around 0 momentum. And it's just sitting there. Cool. Now let's apply a force. What happens? As we apply a force, a constant force with a positive sign, Q is going to increase. So the central value, I should say, so the central value of our wave packet is going to go from 0 to something slightly positive. Because Q is increasing. What that means is that the velocity is increasing first. So the velocity is going to increase, and in equal units of time, it's going to march linearly along this way. So the particle is going faster and faster and faster and faster. And that makes sense. You're driving system by putting an constant force. Of course it accelerates. The velocity accelerates linearly, so the position accelerates quadratically. So let's plot the position. Expectation value of position is a function of time. At 0 time, it's at the origin, it's some trivial position x naught. As we increase time, the velocity is increasing linearly for a while, and the position is going to increase quadratically. Remember that? But eventually, at some point in time, the velocity, or the Q is going to get to the point where we're at the maximum velocity. And at that point, what is the curve for x going to look like? It's going to have an inflection point. Okay? And as we wait longer, Q is going to continue linearly increasing, which means the velocity is going to slow down. So the thing slows down, so it slow decreases until finally it's got 0 velocity again. There we go, 0 velocity, dx dt. And then what happens? We keep forcing it. It's a constant driving force. But this is this, a period Q. And the thing is, we increase Q further linearly in time. As we increase Q further, the velocity becomes negative. So instead of continuing to accelerate, instead of continuing to move in a positive x direction, it starts going backwards. That's weird. You're putting a force in this direction, and it's accelerating in that direction. That's a strange effect. And as we continue, eventually we get to maximum negative velocity, again, an inflection point. And
so I'm gonna pause right now just because I have some work stuff that's coming up. So it's a little bit of a shorter session. I just did 2 hours this morning, but I might be able to put in another hour to compensate in the afternoon. But I'm gonna take a little break right now just because I've got some work I've got to do. I've got an important call coming up. So I will be taking a little break right now. And then when I come back in the afternoon, I think I'm going to switch to working on problem sets. I have managed to go through quite a bit of the things that I'd written down that I wanted to understand better. So I think now it's time to focus on the problem sets. I might even just consistently focus on them for, until some more concepts come up, because I'm feeling okay. I feel like I've kind of rung the Feynman technique. I've squeezed out whatever juice I needed to get out of that from these ones here. There's still some remaining small concepts that I might cover, but those might be better covered by doing the problem sets again. So I think I'm going to go in and tackle the problem sets, and I might focus on that maybe exclusively until I make considerable coverage in there, and then maybe circle back, because it looks like things are kind of coming together on some of the weak points that I had identified. The only thing I really need to do now is go back to the problem sets to get that kind of picture covered a little bit better. So I'm going to take a break right now. I will be back this afternoon to continue studying. Thank you for following the project.